Okay, guys, so I'm sorry that I'm not here again today. Just know that the only reason is because I just feel really, really awful. And it would help me out so much if you could try and pay attention during these notes and stay focused so that when I do get back, we can keep moving on with the process. So the teacher, whoever's subbing, if you need them to pause so that you can take notes, just let them know and they'll pause the notes, okay? Alright, so let's talk about acids and bases. This is going to be our second to last topic, okay? So acids are the things that give food a tart or sour taste. They react with chemical dyes, which we call indicators, to give a color change. And depending on the indicator, depends on what the color change is going to be. They like to react with metals to make hydrogen gas, making that a single displacement reaction. So we've done that in the past, where you have a single displacement reaction and an acid is being worked on with metal. The metal comes in and displaces the hydrogen to make hydrogen gas. So you guys have seen that before. And reacts with hydroxide ions, or OH ions, to make water and a salt. And we can make strong or weak aqueous solutions. So you can have strong acids or weak acids. An example would be vinegar, which is a weak acid. So we'll get into that when we start talking about acid strength. Now, bases, on the other hand, are bitter to the taste, but often are too hazardous to eat, so something that you wouldn't necessarily know. They feel slippery to touch, so when I spill base on my hands, I can always tell because my fingers feel super slippery. They also react with indicators to give a color change, and again, the color change is specific to what indicator you have. And also, they can be strong or weak aqueous solutions, so we can have strong or weak bases. Milk of magnesia, for example, is a weak base. Now, we like to classify our acids, and one of the ways that we classify them is by a guy called Arrhenius decided to classify acids, and he did it this way. Arrhenius acids are described as hydrogen-containing substances that will ionize, or essentially dissolve in water, to yield an H+ ion in aqueous solutions. So when we say ionize, what that means is you take a compound and you dissolve it in water, and it breaks up into its ions, associated ions. And in order to be an acid, one of those ions has to be H+. Now, we like to talk about these because different compounds contain different number of hydrogens, and so we like to talk about them and name them in a certain way. Now remember, a hydrogen is the same as a proton. A hydrogen atom is the same as a proton, and so we like to think of them as one hydrogen means it's monoprotic, or single proton. 2 hydrogens are diprotic. 3 are triprotic, and many hydrogens meaning polyprotic. Note that not all hydrogen-containing substances are acids, and not all hydrogens in an acid will be ionized, only those found in very polar bonds. So we're going to have to think back to polarity. Okay. So, this is what I mean by ionizing. The HCl is dissolved in water and it becomes H+ and Cl-. Now, when I'm talking about the ionizable versus not ionizable, if we look here, this is ethanoic acid, okay, C2H3 or C2H4O2, okay. There are hydrogens in this compound that are not ionizable. The hydrogen here is not a very polar bond, right? Carbon and hydrogen do not have a very polar bond. However, so it's not ionizable. Those hydrogens are not going to break off. However, the hydrogen attached to that oxygen is a very polar bond, and it would be ionizable. And you'll get familiar with addressing and identifying these. Typically, carbon-hydrogen bonds are not ionizable, and oxygen-hydrogen bonds are. If you look at this is methane, right? It's a hugely hydrogen-containing compound, but it is not an acid. Because again, that HC bond is not very polar, so it's not ionizable. But HCl, on the other hand, that is a very polar bond, and that is ionizable, so this is an acid. So if it's not ionizable, it's not an acid. If it is, it is. Okay? And you can contain ionizable and non-ionizable hydrogens in the same compound. Doesn't mean that this isn't an acid. It is, because it does have at least one hydrogen that is ionizable, but not all of those hydrogens have to be. Right. Now, Arrhenius bases are described as those substances that can ionize to produce an OH minus ion in aqueous solutions. So very similar to Arrhenius acids, except for we're producing OH minuses instead of H pluses. These substances can either be very soluble in water or not very soluble in water. Substances that are not very soluble in water will make very dilute solutions, and the OH concentration will be low, so we'll have weak bases. Okay? So if we look at it, here NaOH dissolved in water ionizes and creates an OH minus. Same with KOH. These are both very soluble in water, and so they would make high OH concentration solutions, so they'd be strong bases. Whereas magnesium hydroxide and calcium hydroxide are not very soluble in water and make dilute solutions with low OH concentrations, so they're weak bases. And I'll let you know which ones I want you to memorize, which strong acids and strong bases I want you to know. But right now we're just kind of getting introduced to the idea. Now, the thing is that Arrhenius' definition was very narrow and left out some solutions that showed acidic or basic properties because they didn't fit into the specific definition. For example, sodium carbonate and ammonia are both basic, yet don't produce OH minus ions. So technically they're not Arrhenius bases, but they are basic solutions. So then a guy came around named Bronsted-Lowry, and he changed the definition of acids and bases to be more inclusive. Now, he defines acids as hydrogen ion donors, and bases are hydrogen ion acceptors. So, for example, if we look at this, we've got ammonia and water in equilibrium, and the ammonia here goes from NH3 to NH4+, meaning that it accepted a hydrogen ion. So the ammonia would be a base. The water went from H2O to OH minus, so it donated a hydrogen, so it would be the acid. Again, the base was the hydrogen ion acceptor, the acid was the hydrogen ion donor. So you're looking to the right to see what happens with your products, and that tells you what your reactants did. Okay? Now, since there is OH minus in solution, the solution would be basic. Okay? So if we look at this again, let's take a closer look and draw out the compounds. So you've got N with 3 H's and O with 2 hydrogens. And we know that this one will accept another hydrogen, and this one would be willing to donate a hydrogen. This is going to then become NH4+, where this hydrogen went on to this nitrogen and created ammonium, and then was left with the OH minus. Okay? So you can kind of see where the transfer was. Now, when you do that, I'm sorry. Sorry, that probably didn't sound good over the loudspeakers. So now when you have this ammonia and water in solution with ammonium and hydroxide, if you increase the temperature of the solution, it makes the ammonia gas, less soluble, and therefore it will go out of solution. Releasing that ammonia gas is going to shift the equilibrium to the left to try and replace it. See, equilibrium's coming back, causing the NH4+ and OH minus to now make more, which means that those concentrations are going to go down. Now, when those are being used to try and replenish the NH3 and H2O, they now become, in themselves, proton donors and proton acceptors. In the reverse reaction, so the proton donor becomes NH4+. It has an extra hydrogen that would be willing to be given away, making it an acid. And the proton acceptor is going to be the OH minus because it could accept another hydrogen, making it the base. These are called conjugate pairs. let's look at conjugate pairs. Conjugate pairs are pairs of substances that have a common feature. These common features are their loss or gain of specific protons between the pair. A base has a conjugate acid, and an acid has a conjugate base. So if we look at that same example here. Here, ammonia is a base, is a proton acceptor, so it's a base, whereas the water was the proton donor, so it's the acid. On this side, this is now a proton donor, so it's a conjugate acid, and this is now a proton acceptor, so it's the conjugate base. So you can kind of see how an acid has a conjugate base, a base has a conjugate acid. They're the same basic formula, nitrogen and hydrogens, but with different numbers of hydrogens. Hydrogen and oxygen with different numbers of hydrogens. So they're paired up, conjugate base pairs. Okay. Now, if we look at this situation again, you've got a base, conjugate acid, an acid, and a conjugate base. We can look at another example where I've got HCl plus water making an H3O plus and Cl. So here HCl was a proton donor and water was a base. It was a proton acceptor, making it now a proton donor and an acid, conjugate acid, and the Cl would be a proton acceptor and a conjugate base because there's no more hydrogen to give up. So if you look at water, water was an acid in this reaction and then became a base in this reaction. And that's a quality that is called amphoteric. So in these two examples, water acts as both the acid and the base. When a substance can either act as an acid or a base, it's called being amphoteric. And that's a special quality of water. So, acids or bases can be defined in two ways: Arrhenius acids or Bronsted-Lowry acids. Arrhenius acids are called hydrogen ion producers. Arrhenius bases are OH minus producers. Bronsted-Lowry acids are hydrogen ion donors, whereas a Bronsted-Lowry base is a hydrogen ion acceptor. So it's kind of the same, but you've ruled out this OH minus influence because not all bases can make OH minuses. So now you're going to take some time and practice and try and identify acids, bases, and salts. Remember, a salt is just an ionic compound. And you're going to get some practice and a refresher on naming those. So you may need to go back and look through your notes on naming acids and bases. Remember, we did that in between Unit 9 and 10. So after gas laws, but before thermo. Okay? So I hope to be back with you guys soon. Otherwise, do what the sub tells you and have a good day and keep learning and do try, alright? Don't just give up. Try. I'm going to hold you accountable for this information. A lot of it is review. So you can't just assume that since I'm not here, well, that means it's a day that we don't have to learn. No, you do have to learn, and I'm not going to necessarily go back over it like I wasn't there because you learned. I was teaching you right now. Alright, guys, you can stop laughing at me, and I'll see you later.